Can you guys see my screen?
Yes.
Okay. Hi, everyone. This is our final project presentation. It will be on the analysis of file dependencies to enhance system reliability. Our group name is OS Legion, and our group members are Alex, Vincent, and me, Cyprian. So we're looking at the file system efficiency in terms of its long-term reliability. So files vary in usage, lifespan, and importance. So in our project, we're seeking to analyze the file dependencies within a system. And by analyzing specific attributes of files, we can basically rank their importance. And this would help to determine which files should be copied and preserved in the case of like system failure or crash, and then which files can be later deleted and regenerated for use. So our main work that we referenced was the Legend file system. It's basically a file system that has the ability to recover lost files, and it works to prevent data loss and improve reliability. And it works by identifying the implicit replicas by creating a file dependency graph, and it takes advantage of formatted trace logs. It's basically a simulator that was written in Perl to do the work of viewing the file dependencies. And in our project, we take advantage of its processing and parsing of the formatted trace logs. These are the other works that we also referenced. We mainly looked at how they handle file dependencies, strace, and system recovery. So our main design goal was to determine which files are the most important in a program's execution. We consider file access, usage, timestamps, and size, and we basically use programs that generated lots and lots of temporary files. So in our first attempt, we used some of the scripts from the Legend file system, and we realized we need to generate some more information on top of that. And so within our final attempt, we were able to write our own code that was able to parse the trace logs to get the additional information.
Okay, so a little bit about our parser. Before I go into the assumptions here, so we wrote it in Python using Google Colab, and we picked this because Google Colab is a really great way for most people to work on a single piece of code. Python is a really good scripting language, hence the choice. It's about 500 lines of code roughly, and essentially we picked some certain syscalls, which I'll kind of go over on the slide. We sort of monitored file usage during an strace log. The first one is that we essentially ignored fail calls to open at and open, and essentially in an strace log, often you'll see an attempt to open a file, and that results in -1 return value. And so we consider that not to be used by a program. We treat libraries as a single file. Now, obviously, libraries contain far more files, but for time's sake, we just consider it as a single file. We can kind of estimate the return or the size of a file by read. There's obviously better ways to do this, but if you're solely using strace, this is sort of the best predictor of a file size. We ignored all instances of IPC, including pipes and sockets. We're only interested in files. For file access, we define this as an instance where a call to the open at or open function succeeds. We consider file usage to be defined as successful calls to the mmap and read, which essentially sort of use the files. For 7 to 8, right, we have certain heuristics we use if certain files are temporary, such as being in the temp file, or the ld.so.cache is regenerable when ldconfig is called. And some of these straces that was called many times. So a little bit about the implementation. I talked about this. What's kind of nice about Google Colab, it's a nice modular setup, so you can run the different like sections of code separately. If we have some time at the end, we can sort of demonstrate this. The addendum sections is essentially the work we had done earlier with the Legend file system scripts before we went on writing our own code, but we felt it was useful to put this in just so it would help elaborate our design choices in writing code. Next slide. So we're going to go over some of the graphs that we rendered, but these are a couple of things that sort of stood out in the research. Often what's sort of temporary is not automatic, right? And this comes down really to sort of the application and having sort of specific knowledge about it. Like, for example, when we did Mozilla Firefox, there's a specific folder called morgue, which all those folders can be regenerated, but that's not always consistent across all web browsers. Different applications, widely varying file usage. Some use a lot, some use very little. Something interesting, timestamps oftentimes did not translate to file importance. Many times temporary files would have high timestamp usage. And so this sort of kind of threw our definitions a little bit off. And then one pattern you'll see in the graphs is more files are accessed with lesser frequency, but less files are accessed with higher access frequency.
All right, here is a view of a bar graph that contains the frequency of file access of strace of a makefile that compiles past C, C++ school projects. As you can see, there are singular files accessed multiple times, and there is one file that with the most access times of 64, and it's actually a library file. There are total, like max 114 files that were accessed only 2 times based on the strace log that was parsed. Next slide. Okay, this is an strace of an application which is actually on Discord. So this graph follows a trend of some singular files being accessed multiple times and has 332 files only accessed once. There is one file with the most access time of only 25, which is also a library file. And then the next is actually an strace of the web browser. This is of Firefox while accessing Amazon. The browser strace log has a different distribution with more files being accessed multiple times, with 371 files being accessed only once. There is still a trend of many files being accessed like once or twice. Now, this is a table that takes a looks at the number of files used, number of ignored files, number of temporary files, and percent of files that are temporary for our makefile straces. I know in makefile 1 has multiple files compiled and could be a contributing factor to the higher number of used files. And makefile 3 has a lot more ignored files than any other makefile strace logs. Now, this table consists of data traces from the browsers Firefox, Chrome, and Opera. Their numbers are much higher than those of makefile traces. Browsers seem to have a high number of used files. Opera and Chrome use more files, but Firefox has a higher percentage of temporary files. The number of used files seems like it could correlate to the amount of activity that is going on in the browser. And then this is a look at the traces of the applications we looked at. So we have one for Discord, Nano, Vim, Audacity, LibreOffice, and Deluge, which is a torrent client, and Telix, which is a terminal. So in this Deluge torrent client was seeding, and Discord was being used by talking to my group members. So it seems like they have higher numbers because of the activity was going on in those programs. And then with Nano, Vim, and Telix, these programs were just opened and closed. So you can see probably it correlates because they have smaller numbers. And then these are pie charts that contain the distribution of ignored files, regenerable and non-regenerable files from the traces. And they are samples taken from the first 3 straces that we used in the earlier slides. The first 2 pie charts are for the makefile and application traces, and they look very similar and show a high number of ignored files and a small number of regenerable files, with the close to a quarter of the files being non-regenerable. And the browser strace has a higher percentage of non-regenerable files with a decrease in the ignored files and increase in regenerable files. And those are usually containing temporary files.
Okay, so sort of what did we do? Inevitably, time was our biggest enemy, and we fell a little bit short of our final goals, but nevertheless, we felt that we have presented sort of sufficient sort of work that can be not only used for our conclusions, but for other people's research. We have provided working strace parser code that essentially can be used and modified to anyone who'd like to use it for the public benefit. And we've also created visual representations of the file frequency, which we find is an important piece of information. Possible uses of our research, anyone else who wants to do research on sort of file recovery and reducing overhead of file replication. Kind of an interesting sort of non-file related use that we actually could be done is if you're sort of where a malware analysis do is when you run a piece of like a virus or a malware in a sandbox, right? You sort of want to track what that does on the system, sort of how this affects system files. And so actually our parser is well set up to track an executable via strace to see like if a piece of malware, what system files it affects. And then possibly it could be useful to write better code and programs to efficiently connect IO. As we saw on the pie chart on the previous slide for the make files, there's a lot of failed calls to open at, and that's using a lot of system time making, I see like the make file 1. So we feel that this could help maybe write possibly better code at the higher level to sort of spend less time on making failed open at calls.
And some future work we could do to build upon this is to have improvement in identifying the files used specifically within libraries. We could incorporate the scripts into an end application, and we could incorporate the timestamps and size as a bigger factor like used to determine importance. And then we could automatically identify temporary files without the need of heuristics. And a deep learning model could possibly be built from the data that we gathered. Here are our references, and that is all. Are there any questions?
Any questions from the audience? Okay, next group, please.